Hello again. Welcome back to Tux Theater. Next up, we have Paul McHarris to talk to us about Microwatt. Paul McHarris is a senior technical leader in the IBM Linux Technology Center. Currently, his main responsibility is as architect and maintainer for KVM on IBM Power Systems and on Power architecture machines more generally. He is one of the main contributors to the Microwatt open source Power ISA softcore. He also contributes to the definition of the Power Instruction Set Architecture, ISA. So Paul is hoping to have time to take questions at the end. So hopefully by now you're familiar with the questions tab there next to the chat, underneath where the video appears in the stream. So please put your questions there and we'll pass them on to Paul at the end if there's time. Welcome, Paul.
Thank you, Betsy, and good afternoon, everybody. I'd like to tell you this afternoon about Microwatt and what we've done in the last year or so. Microwatt grows up, so it's become much more mature and capable, and I'd like to tell you what that involved and what it can do now. So Microwatt is an open source CPU core which implements the Power Instruction Set architecture. Microwatt is written in VHDL 2008, and it was initially written by, or started by, Anton Blanchard when the announcement for the Power Instruction Set architecture being opened was being planned. And that announcement happened in August 2019. And Anton wanted there to be at least some, even if it was a tiny example of an implementation of the Power ISA that was open source, and people could look at it and play with it and work with it and develop it and all that kind of thing. So Anton, being basically a software engineer, had to learn VHDL for a start, and so he did, and he wrote a core that basically implemented the integer part of the instruction set and pretty much just the user instructions. But being a software engineer, he wanted to use the software engineering techniques that we've become used to with things like the Linux kernel and other open source projects, where we have good tracking of the source code using Git. We've got a disciplined process for updating that, and in particular that we've got quite a bit of automated testing so that we can catch bugs early on. So we're not going to write code for 3 months and then say, okay, here's this big lump of stuff, and merge it and then find that it's got all sorts of bugs. We're doing a more incremental development and testing, with unit tests and with larger tests, functional tests, to make sure that we're not regressing the code. So it's hosted on github.com, and we now have GitHub Actions that run a bunch of simulations and also do a synthesis for an ECP5 FPGA. Now, Microwatt is targeted mostly for both simulation and for FPGAs, so synthesis for FPGAs. And the FPGAs that we're targeting are what I would call kind of a mid-sized FPGA, not the really tiny ones, not the really big enormous ones, but the middle of the range. So things like the Xilinx Arctic 7 and the Lattice CCP5. And this is the range where you can get hardware that has these FPGAs that is, ranging from, I guess, 20, 30, 50 up to a few $100s. So the board that I mostly use is this one here. It's called an RDA7. This that comes in two variants, one which has a 35T FPGA and the other one has a 100T, and this one's got the 100T. And that's actually been really good because Microwatt on the 35T is pretty much starting to fill it up now, but on the 100T it's like 3 times as big, so I've got plenty of room to play and do things like the floating point unit and start to implement vector instructions, but I'll talk about that later. So we use GHDL for simulation. GHDL is a GNU, it's a GPL licensed piece of software. VHDL is actually based on Ada, which I didn't know before I started looking at it. So GHDL is an extension of GNU Ada. For the Lattice CCP5, we use GHDL plus open source place and route type tools, Yosis and NextPNR. These tools are based largely on reverse engineering of the lattice bit stream. For the Xilinx Arctic 7, I at least still use Vivado, which is Xilinx's proprietary tool. Fortunately, there are free licenses available for that. I would like to use free tools, but they don't quite seem to be there for the Xilinx parts yet. There seems to be a lot in them, in the Xilinx parts, that's difficult to work out about how the bitstream works from reverse engineering, at least. That's the impression I have so far. But I would really love to have open source tools there that we could use as well. Now, the Microwatt Core has a wishbone memory interface. That's a particular style of how to connect to memory. We use peripherals from the Litex project. That's a project which has a whole pile of different kinds of things. It's got DRAM controllers and Ethernet and SPI and SD card and all sorts of different peripherals. It's all wrapped up in object-oriented Python, which I personally find a bit difficult. And it likes to create a whole SOC, not just a peripheral that I can then take and put in with my other stuff. So, nevertheless, we've worked around that, and we have an Ethernet and a DRAM controller from the Litex project. So that's all great. We've got this core that can run integer instructions and user space instructions, and fine. But we're all Linux programmers, so we really want to run Linux on this thing. What does it take to run Linux? So that's the main thing that I'll be going on with later on in this talk. Firstly, though, I'd like to just recap the basic features of the power instruction set architecture. It's a 64-bit RISC architecture. I wrote it had fixed length instructions, but then, of course, for Power 10 and version 3.1 of the ISA, they added these prefix instructions. And if you went to Jordan Neither's talk earlier today, he explained about those and what the advantage of those are. We haven't actually implemented them in Microwatt yet. So as far as Microwatt's concerned, we still have fixed length 32-bit instructions. We say it's RISC, and there are a number of characteristics. Having a small number of instructions is not one of them. This ISA does have quite a lot of instructions. But there are characteristics such as that only the load and store instructions access memory, and basically the load and store instructions don't do anything except accessing memory. You have a lot of registers. So the register set has 32 general purpose registers, GPRs, each of 64 bits. It has 128-bit vector scalar registers. It has 64 of them. The 32 floating point registers that have been in the architecture for a long time are incorporated into that sort of 64 by, as one corner of that 64 by 128-bit square of VSRs. There are also what we call special purpose registers. These include some things that get used quite frequently in programs, such as the link register used for procedure linkage, the count register, which is used for tight loops and a few other things. But then there are also many special purpose registers that relate to features of the system that are accessed more rarely, and they include things like a data address breakpoint register and registers in the memory management unit that tell you the address where a page fault happened and that kind of thing. And there's also a 32-bit condition register. Normally, you'd expect a machine to have some sort of condition code register or condition codes in some register, and there's normally 4 bits of condition code. But the power architecture's got 8 sets of 4 bits. And what this does is it lets you decouple a comparison from a branch, for instance, so that you can do a number of compares and then later on branch based on the result of those comparisons, and you can hide the latency between the compare and the branch in that way. Finally, there's what's called the machine status register, MSR, which is one of those examples of IBM using an acronym for something different to what the rest of the industry uses, which we do quite frequently. But the MSR contains bits like Are you in privileged mode or not? Are interrupts enabled or not? Is the MMU enabled or not? That kind of thing. Now, instructions have between 0 and 3 register operands. An example of one with 3 operands would be a multiply add type instruction. And it has 2 addressing modes for accessing memory. There's what's called offset mode, which is that you take the value in a register and add a constant to it, where the constant comes from the instruction. And there's indexed mode, where you have 2 registers and you add the contents of the registers together to get the value that you want, the address that you want, what we call the effective address. Now, the power instruction set architecture has actually been around for a very long time, since the early 90s, in fact. You may well know it as PowerPC, because as Hugh explained in his talk that he gave earlier on about open power, it was initially power when it was an IBM thing, and then when the Apple, IBM and Motorola consortium was launched, the architecture was revised and it was called PowerPC. And it was known as PowerPC for a long time, and it's still called PowerPC in the kernel tree. For instance, it's Arch/PowerPC. IBM renamed it back to Power basically after Apple stopped using it, and Motorola/Freescale/NXP very much stopped using it so much, and so then it became pretty much just the architecture for the IBM Power server machines, and so it was renamed back to Power ISA. So we have a number of versions. Version 1.1 is the thing that was in the 90s. It was 32-bit basically, although it had 64-bit as an extension, and it was used for a lot of the chips that Apple used. Version 2.0 corresponds to Power 4, so that was in about 2000 that Power 4 came out, and there's a correspondence between releases of the Power processors and versions of the architecture. We go from version 2.0 for Power 4 to version 2.07b, which is Power 8. Then version 3.0b is Power 9. And the interesting thing about that one is that it adds the Radix memory management unit, which I'll talk about later. Then in version 3.0c, which was a minor revision, they added, this was after basically the architecture was opened, or in conjunction with it being opened by IBM, they added compliancy subsets. And the idea here is that in opening up the architecture, we expect that people will use it for all sorts of different things, and that for some applications you may not want to implement everything that a Power 9 implements. So you can implement what's called, for example, the scalar fixed point compliancy subset, which says that you have to implement all the basic integer instructions and a bunch of other stuff, but you don't have to implement floating point, you don't have to implement the vector instructions, you don't have to implement various other things. Then in particular, you don't have to implement the hash page table MMU. There's also a scalar fixed point plus floating point compliancy subset, which is like SFS but adds just the floating point instructions. And then there's what's called the Linux compliancy subset, which was intended to be kind of the minimum that you would need to run Linux. In fact, it turns out you can run Linux with less than the Linux compliancy subset, but I'll talk about that later too. And then with version 3.1, that corresponds to Power 10, and we get the prefix instructions that Jordan talked about, and we have now some instructions that are 64 bits long. But as I say, I'm going to ignore them because Microwatt doesn't implement them yet. Okay, so we want to run Linux. We're all Linux hackers. What's the point of a processor if you can't run Linux on it? Yeah, I know, but let's go with that. So the first thing you need privilege modes. You need to be able to have a kernel that's running and is protected from what user space does, and you need to be able to protect, one user space from another user space. So you need to have this concept of user mode and kernel mode or supervisor mode, which in the architecture are called privilege state and problem state. Problem being because that's you're running user code to solve some problem. So that's why it's called problem state. And then you have interrupts or exceptions or traps. These are different names that people use. In the architecture, it uses the word interrupt a bit differently from how it's used in the rest of the industry. Another example of how IBM likes to do this. But it is used quite precisely in the sense that the interrupt is the change in the flow of program control. In other words, the interrupt is the act of stopping executing the instructions that you were executing and saving a little bit of state and starting executing again from an interrupt handler. So that applies to things like external device interrupts or timer interrupts, but it also includes things like page faults and system calls and interrupts that your program might cause by trying to execute a privileged or illegal instruction. Or it could also be something like a debugging interrupt where, you've done a single step and you've executed one instruction, so then you go to the single step handler and that's an interrupt. Or if you execute a trap instruction, which is like a software breakpoint, that's an interrupt. The exception then is, in the architecture, is the condition that causes the interrupt to be taken. So the exception is, for instance, that no valid PTE was found, no valid page table entry was found when trying to translate an address. That's an exception. And then the interrupt is we jumped to the 300 hex address, which is the data storage interrupt handler, where you handle a page fault. So we need them because that's how you get out of user mode back into the kernel, and that's how you enable drivers, for instance, to function while user space is running. So we need those. We need a memory management unit. We need an external interrupt controller. There's basically a single wire that comes into the CPU that says there's a device needing an interrupt, and you need some way to be able to control whether devices can interrupt. And in an SMP system, you need to be able to control where those interrupts go and that kind of thing. And finally, we need enough memory. For a Linux kernel, that's going to be at the least several megabytes, and preferably quite a bit more than that. And the more the better, really. Okay, so to implement interrupts, this is one of the first things we did early last year. In fact, Mikey Newling did most of this work. So we have in execute1.vhdl, we have logic that detects the exception condition that's arisen, and then we arrange to do the steps of taking an interrupt, which is that the instruction address where we were up to gets written to this SRR0 special purpose register, and the contents of the MSR plus some extra bits to say what the cause of the interrupt was, etc., get written to SRR1, and then we basically branch to the interrupt vector address. So that's fine, we did that. Mikey also wrote the external interrupt controller. Now, there's a number of different possible ways you can organise an external interrupt controller. We chose to use the one called XICS. This is not the one that's on Power 9 and Power 10. It's the one that preceded that was used on the IBM Power machines, basically from Power 4 until Power 8. It comes in two parts. One is that there is an interrupt controller source per interrupt source. So every possible device that can interrupt, every interrupt line that comes from a device would have an ICS register, and that lets you control the priority of the interrupt, where it goes to, and turn it on and off. Then for each CPU, you have this ICP, interrupt controller presentation, set of registers, and these say what the priority of the CPU is, and by reading them you can acknowledge an interrupt, and by writing you can cause an interprocessor interrupt where one CPU just wants to generate an interrupt directly to another one. So it's actually pretty simple. It's way, way simpler than the XIVE that was introduced with Power 9, and it seemed like a good fit for Microwatt. Now, as for the privilege modes, there are 4 modes defined in the ISA. We have ultravisor, hypervisor, privileged non-hypervisor, which I normally call supervisor, and problem state, which most people usually call user mode. Hypervisor is there for virtualization, so that you can have multiple virtual machines. So you can do, you can have logical partitions, or you can run KVM, that kind of thing. The ultravisor is there for a kind of trusted execution environment type of facility. So I'm going to ignore ultravisor and hypervisor. In Microwat, we just do supervisor and user mode, and there's one bit in the MSR that selects. That's the PR bit, and when that bit is 0, you're privileged. When it's 1, you're in problem state. So what do we do to implement that? Well, we have to add logic into Microwat so that we know for each instruction whether it's a privileged instruction or not. And if it's a privileged instruction and MSR PR is 1, then we don't execute the instruction, we generate a privileged instruction interrupt instead. Then the interrupt, of course, clears MSR PR, so then you are in supervisor state, and you can handle it. And finally, once we get to an MMU and we have PTEs, page table entries, they have a privileged bit. And if you're in user mode and you try and access a page where the PTE says privileged, then once again you take a page fault. So we did all that. Then we come to the memory management unit. Now, our instruction set architecture defines 2 different address translation schemes, as I mentioned earlier. We've got the hash page table. This is the one that's been there since the beginning. It's used by IBM's proprietary operating systems, AIX and IBM I, and it's also used by older Linux kernels because the radix page table was added, as I said, in the ISA version 3.0 for Power 9. And so before we got to the point of starting to support Power 9, there was no radix page table support. So if you're running a kernel that's, let's say, 4.5, version 4.5 or older, it doesn't have the support for radix page table, at least not unless your distro has backported all of that stuff into its older kernel, like Red Hat did with the 3.10 kernel. That was a Franken kernel. Anyway, so older kernels don't know about radix. Newer ones do know about radix since about 4.6 and prefer to use radix. In fact, the radix page table was added to Power 9 specifically for Linux, and Linux is the only operating system that uses it. So it actually improves things quite a bit for us because we can map the kernel's architecture-independent radix page tables, which it's always had, onto the hardware so that the hardware can read those radix page tables directly. So that was a big win for us. So Microwat, of course, implements radix and not hash page table. Radix, I think, is generally simpler and requires less hardware, and it's the better way to go for Linux anyway. Now, the ISA defines a very general tree structure here, and I'll just walk through it because it's quite interesting. At the start, you have on the left this partition table control register, which is an SPR, and that points to the partition table. The partition table is in memory, and it's indexed by this logical partition ID register. So this is used for virtualization and enables you to have different page tables for each different guest, each different KVM or PowerVM guest. The partition table entry then points to the process table. This process table is in memory, but it's in the guest memory if you're running in a guest. And it's indexed by the process ID register. Now, this PID register is what the kernel changes when it switches from one process to another. So each process has got a different value for the PID register. It's got a different entry in this process table, and therefore each process uses different radix page tables. And then entry 0 is used for the kernel. So the MMU has got a arrangement where it looks basically at the top 2 bits of the effective address that you generate, and if those are 1, 1, then it's a kernel address and it uses entry 0 here. And if they are 0, 0, it's a user space address and it uses whichever entry the PID register is pointing to. Then that process table entry points to these smaller boxes I've shown here, which are the radix page tables, and they're indexed by the by bit fields out of the address. So you're taking the effective address and you're selecting, series of bits out of it, and those series of bits are used to index each level of the tree. This is just how radix page tables work. And then at the end, you get to something that points to the page of memory that you're actually wanting to access. So I'll just go into a little bit of detail here about these page directory entry in the top levels of the tree, just to point out that they have this NLS field, which is the next level size. So the architecture has not actually hard-coded that the page size is 4K and that you then have a PMD level that maps, let's say, 2 megabytes, and then you have another level that maps a gigabyte, and you have another level that maps 512 gigabytes or whatever it is. As far as the architecture is concerned, the programmer can set up whatever fields it likes to be the ones that are indexed out of the page tables, out of the effective address to index the page tables. So you could have 2 levels and just map 2 gigabytes, or you could have 10 levels and map 4 exabytes or something. The hardware engineers, of course, when they saw that, threw up their hands and said, this is totally impossible, we can't cope with this. So the ISA does define 2 standard layouts, both of which have a 52-bit effective address. And notice that that's 52 bits for user space and another 52-bit space for the kernel. So it's a bit different in that you get to use 2 different trees, one for the kernel and one for your current user space process. 52-bit effective address, 4 levels, and a 64K page size is the first standard layout. So your index fields index 13 bits, then 9 bits, then 9 bits, then 5 bits, or one with a 52-bit EA and a 4K page size where you use 13999 bits. However, when we came to do this, or I came to do this, in fact, for Microwatt, I thought, why not just, since we're going to do a state machine that's just going to walk through the levels, and I'm not trying to do a very highly optimized implementation, why don't I make it so that it will actually just take whatever layout you like and just process that according to the architecture and work out the translation? So I did that. So you can have any address, in any NLS value at each level of the tree between 5 and 16. You can have any size for your total address space from 31 bits to 62 bits, and any pair of 2 page size that you like from 4K upwards. And that, if you work out the math, that means that you can then have any number of levels you like between 1 and 10. So we did that. That turned out to be, it performed surprisingly well, let me put it that way. So what we did is we added level 1 TLBs to instruction and data caches. So these are actually integrated in along with the cache tag lookup. So in parallel with the cache tag lookup, it's doing the TLB lookup, and then at the end it's comparing the results and saying, yes, we've got a TLB hit, that gives us a real address, we've got a cache hit for that real address, and we can access the cache, or maybe not, and then we get a page fault. Well, we don't get a page fault. We have to go and then ask the MMU to look up the PTE. So that's that looking up the TLB and the cache tags in parallel is a pretty standard technique. But it meant that we didn't add any latency to the cache for having the address translation. So we have a 4K byte page size in the level 1 TLBs. Instruction TLB is direct mapped. It has 64 entries. The data TLB by default is two-way set associative with 128 entries. And then the MMU is a state machine that gets kicked off when there is a miss in the instruction or data caches, or in fact, a protection failure also kicks off the MMU. So the MMU actually doesn't do any caching. It just starts, well, it caches the process table entry. It doesn't cache any of the PTEs or PDEs. So it sends a series of requests to the data cache, basically works out an address, takes the next bit field of the address, works out the address of the PTE, sends that off to the Dcache, gets the value back, uses that to construct the next address. Eventually it gets to a leaf page table entry, and then it sends that translation that it's calculated to the Dcache or the iCache, and then the iCache or Dcache can proceed with the access. Or in the case where there was not a valid PTE or there was a protection failure, then we trigger a page fault. But as I said, there's no caching of page table entries or page directory entries in the MMU. Normally with a radix tree walker, you would have quite a bit of caching, including a thing called a page walk cache, which is pretty essential for good performance. We don't have that, but still it works. It performs more or less okay. And we don't implement the partition table because we don't have virtualization. Instead, we just have a pointer to the base of the process table. Okay, so that's the MMU. Now, the next thing we need is more memory. So Ben Herrenschmidt actually did most of this work early last year before he got really busy with real work. So he adapted the Light DRAM controller code from the Litex project because they'd had a Light DRAM that was pretty capable and knew how to control the DRAMs, the SDRAMs that we have on the ARTI board and that kind of thing. The ARTI A7 board that I use has 256 megabytes of SDRAM. And Ben also did a level 2 cache, which is integrated into the interface between Wishbone and Light DRAM. So this level 2 cache is actually quite nice. It has a 128-bit interface to the DRAM controller. That means that we can suck data out of memory into the level 2 cache more quickly than if it was 64 bits. And then it supplies the data in 64-bit chunks on the Wishbone, which is 64 bits. It includes an 8 deep store queue, and it has 128-byte line size. It's 4-way set associative, and it's 32 kbytes in total. It actually gave us, this level 2 cache gave us quite a good performance improvement. Next, the floating point unit. Why do a floating point unit? Well, it's in the architecture. You don't have to do it, but it's there, so I thought it would be interesting. More particularly, we don't want to have to define a soft float ABI. We did have that in the old days of embedded 32-bit PowerPC, and it just fragments your ecosystem and makes it harder to have compatibility of your code and that kind of thing. So I thought, let's try and make a floating point unit that implements the architecture, is fairly simple, doesn't have to be blindingly fast, doesn't want to be, glacially slow either, but let's see how small we can make it. So then what are the difficulties? Well, you have things like divide instructions and square root instructions in the architecture. How do you do a division efficiently? Turns out that there are interesting numerical techniques that you can use, particularly for things like square root. Things like Newton-Raphson iterations to refine estimates of reciprocals, and you can do one on square root of x estimates as well. And there's a thing called, I think, the Goldschmidt algorithm that iteratively gets you better and better approximations to square root and inverse square root. There's also fuse, multiply, add instructions. You have to handle denormalized numbers and exception conditions correctly, and all of this is specified in the architecture quite specifically. And you need to get the right result down to the last bit in all rounding modes. You have round to minus infinity, round to 0, round to plus infinity, round to nearest. So I did at FPU using a state machine for the control. It only handles one instruction at a time. It's not pipelined. It ended up using about 4,500 LUTs on the Xilinx Arctic 7, which is about 20% of the total system that we have at the moment, or 7% of the A7-100 part. And, add, subtract, take 5 to 12 cycles. It's not, as I said, not blindingly fast, but it's a lot quicker than emulating. Here's a diagram, very much simplified, of the data paths. It took me a long time to actually work out how to organise this in such a way that we could do everything we wanted reasonably efficiently, but without using any more resources than we really need to. And we have the 3 input registers here because we need 3 input registers because we have floating multiply add instructions. They're interesting because you're doing A times B plus C, but it could be that A times B is very close in value but opposite in sign to C, so that the result is very close to 0, and you have to preserve those low order bits, and the floating point multiply add instructions are defined such that you do get a high resolution intermediate product that then lets you get those low order bits accurately. So we have these input registers, we have a lookup table that we use for getting inverse estimates and inverse square root estimates. We have a thing that can do addition and subtraction, and a few other things. And then we have a multiply adder, 64 by 64 plus 128 multiply add. Those results basically go into this R for result register. We have this S is kind of an extension to the R for the low order bits of the product here. And then we have P and Y, which are involved in the iterative algorithms for divide and square root. So they let you do the iterations of the Newton-Raphson or Goldschmidt algorithm. Then we have a thing that can count the number of zeros at the left-hand end of a word so that you can do normalization. We have a register that stores that, and then we have a shifter, and so we can put values into R, we can shift them, we can add things on, or we can give constant values like infinities and so forth, and then we send that to writeback. Another interesting thing that we added to MicroWatt is a hardware random number generator. There is an instruction called DARN. It stands for deliver a random number. I'm sure someone was very pleased with themselves when they thought of that acronym. So the DARN instruction can return either raw or conditioned random numbers. And I went looking on the web and I found a paper by Cattell and Bertoniu called High Speed True Random Number Generators in Xilinx FPGAs. It sounded like just the ticket. And indeed, it turns out to be a very interesting circuit. We have this set of coupled ring oscillators here. These are exclusive OR gates. And what each one is doing is it's XORing itself and its 2 neighbours, and it wraps around as a ring. And then just to ensure that there isn't a stable state, this XOR on the left, one of them has got an inversion. So that's an exclusive NOR. So this is all completely unstable and completely impossible for the tools to analyse the timing of, because there's no stable state. They basically all just oscillate chaotically at gigahertz speeds. And then you put that through a register that samples at your clock rate, which in our case is 100 megahertz, and you get actually pretty nice random numbers out of here. And the DARN instruction can read from this level here after this top, just the coupled ring oscillators, or it can read these conditioned ones out of the linear hybrid cellular automaton, which is a kind of relation of a linear feedback shift register, an LFSR. These DN things should be shown as AND gates, really, because you either put 0 in or you put the value from that register in, and that defines a polynomial that then defines the behaviour. But it's all in that paper there, and I basically just implemented what was in the paper, and it generates really nice hardware random numbers. So then we hacked up the kernel. I'm running out of time, so I'll proceed pretty quickly here. We defined a new MicroWatt platform, which longer term we probably don't want to do. We'd probably like to be able to use the PowerNV platform, but to do that we'd need to port Opal, the Opal firmware, to MicroWatt. Now Opal is open source. There's nothing stopping us from doing that except time and energy, that kind of thing. There are some other patches that we added, including the LightETH driver, and we constructed a device tree by hand. This describes CPUs, memory, interrupt controller, peripherals, etc. We create a DTB image and we put that in SPI flash. We have console on serial port, and then either a RAM disk or an NFS root. And the stuff, the code is all there in Ben's branch, although he hasn't updated it recently. So what can we use it for? Well, one of the things that we're looking at is doing a baseboard management controller with it. And we're going to replace the BMC in a Power 9 server with one of these RDA7 boards with an adapter. And, we want to find out, is microwatt small enough, fast enough to be practical, and just demonstrate that it can be done and it can work. Raptor Engineering, as Hugh mentioned in his talk, has got a similar project underway, the Kestrel project, and we're doing something fairly similar. They're in fact also using the microwatt core, but we will probably have a full Linux running underneath it. Okay, what else can we do? Well, there's a chip. This is a picture of what Anton's been working on for about the last month or so. If I just go to here, this is a description of the OpenMPW shuttle program. This is sponsored, paid for by Google. Basically what they're doing is they're saying if you have an open source hardware design, you can get it put onto a chip and we will make the chip. It's an old technology, it's 130 nanometers, but it's a chip, it's a real chip. So that's what Anton's been working on. And where next? Well, there are a number of things that we'd like to do. 32-bit, add a vector unit, add a performance monitor, do SMP, add hypervisor mode. Eventually we'd like to get to actually implementing the complete architecture and see if we can do that in a modest-sized FPGA. Finally, what I'd like to do is just demonstrate Linux booting on my little RTA7 here. So what I'm going to do is I'm going to run a command that this XC3S prog, it's going to load a bit stream that I compiled earlier onto that RDA7 board. And so I do that, and then I'm going to run Minicom, which will connect to the serial. And we see some boot messages. We're decompressing the kernel. We're booting Linux. Now I'm using an NFS route here, so basically the pause here is that it's fetching a whole pile of stuff over NFS, and it's the Ethernet is 100 megabit, not gigabit, so a little bit of latency there. But I mean that makes it easy for setting up and also recovering if the thing crashes. So I can log in. I can cat proc CPU info. There it is, microwatt at 100 megahertz. I can do free. I've got 256 gigs of memory minus a bit. So there we are, Linux running on that board. So thank you very much. Do we have questions?
All right, thank you, Paul. We have quite a few questions in the list, but I'm expecting that we only have time to answer one of them. Because we have 2 minutes left. So here's one of the questions from earlier in your talk. You have adopted good software engineering, testing, and iterative improvements with changes being tested. Have you seen any CPU designers from other areas watching your project adopt any of this to improve their own processes yet?
Yeah, that's a good question. It's a little hard to say. Certainly, people like the LibreSoc team are also using good software engineering practices, but I wouldn't say that they necessarily got it from Microsoft. In terms of, do I know of any hardware engineer who's reformed his ways? Yes, I mean, the guy that has been pushing the A2i and A2O cores, I think has been starting to adopt some of these practices.
That's great. I think probably most of the other... Oh, here we go. Let's do this one. Is the hardware random number generator suitable for use in programs where security is important?
I think so. I think that using a hardware random number generator like that, that you can actually see the source for, and you can verify, particularly if you're using an open tool chain, that's how the random numbers are generated, that they're not being backdoored by something in the chip that you don't know about. That, in fact, would be excellent for security. And in fact, I've run the full suite of Die Harder tests on it, and it passed everything. Now, of course, with the Die Harder tests, 1 or 2 you get that say, oh, this is a weak result, but then that's just the nature of random numbers, that if you didn't get any weak results, that would mean that your random number generator actually wasn't very good, which is a bit paradoxical. But, those ones that it says are weak, you run the test again and it says, no, that's a strong result. So it was just a random fluctuation. But yes, I have run the entire Die Harder test suite, and it all looks really good.
That's great.
And it only uses like 128 LUTs. It's really tiny.
Great. Okay, we're out of time. There were more questions asked in the chat. So what we'll do is ask you, Paul, and everybody who's in the audience who'd like to join in, to head over to the post-talk Q&A channel for Tux Theatre. It's in Venulus. If you haven't accessed it before, it's in the sidebar on the left. You may have to click Browse All Channels and find Tux Theatre Post Talk Q&A. And those questions that we didn't have time to ask live, I will paste them into that channel for you. It's now afternoon tea time, I believe. I just have to double check the schedule. Yes, afternoon tea time. Enjoy your afternoon tea, everyone, and we'll see you back later.
Thank you.